So let me write the primal LP for this in the way that you don't identify. So F is the solution of the flow, V is the value of the flow, right? So F is the flow vector. This is the flow in every edge. V is actually the sorry? Oh, this will be your constraints, right? The connection, the adjacency graph. This will be some version of adjacency matrix, which will give you, right? So this summation x from every direction, all the edges, it will, I think, be some small version of adjacency matrix. As an exercise, you can figure out what A is. Like you write the flow things, you will figure out A, right? Yeah, you can figure out which one is source, which one is sink. If this still seems mysterious, remember we had the flow conservation constraints. Instead of equality, we had changed it to less than equal, it didn't matter, right? So the previous constraints look like AF less than equal to 0 for all the vertices except S and T. Here we have included S and T. That's all. Flow, this is the capacity constraints, flow has to be positive. Great, right? And now, if you remember our approach, we never have to worry about this, right? Because this was only used to give you the idea of the algorithm. The algorithm runs just here. Find the feasible solution, give me the restricted primal. Solve restricted primal, it will allow me to improve my original solution. Again, this will allow me to create the restricted primal again. This will again lead me to improve. So algorithm just goes this way. It has nothing to do with restricted dual. So why, anyway you are very bad at taking dual. So why write restricted dual? Okay. You are taking restricted dual. This again, the constraints remain the same in the restricted primal. The variables have constraints. I just removed the thing, but so this is where your restriction will come. Okay. Sorry, yeah. So you raise a good point. If you remember, in the restricted primal, some of the constraints were removed. Correct? Why have I not removed any constraint here? Sometimes you pose problems by asking the question, because I will ask the question to you again. Right? So if you remember, this is a constraint, whenever I'm putting them up only when this was tight. Corresponding to that, I have changed the constraint. Right? When this was tight, I have changed the constraint. I have never mentioned about this. If this was not tight, I should have dropped those. Why haven't I dropped those constraints here which are not tight? This has nothing to do with linear program. This has to do with max flow. Remember, originally, this was AF plus dV equal to 0. We said, remember, there is a flow conservation constraint, right? So, for a feasible flow, this will always be equal to 0. It's a flow conservation constraint. We said that we can relax it to be less than equal to 0, but will remain equal, right? In any solution, any feasible flow solution, this has to be 0. It cannot be anything else, right? So, nothing is going to be dropped from here. Okay? But now, one more question to you, even though you didn't make it happen to yourself, I inflict the pain. Do you recognize this LP? This should remind you of something. Huh? S. Very good. You remember this we did in the, when we solved that dual of the ILP and LP were equal, we talked about residual graph, which was we only keep the edges where there is capacity and where there is equal to 0, right? So, we are going to create a residual graph and then see if there is a connection. That residual graph will allow us to move the flow. Okay? So we look at the feasible solution. Wherever for an edge Fe star is equal to C, we say that we can push a negative flow there. Wherever Fe star is equal to 0, we say that we can put a positive flow there. Okay, and these are just artifact of that restricted primal. F less than equal to 1, yes. We had x less than equal to 1, remember, in the restricted primal. So now we have two variables, f and v. Okay, all xi's were less than equal to 1. Okay, so this, and again, most of the time, if you are going to apply an LP solver here, this is mostly going to be a waste. Because this is an LP, this is an LP. An LP solver cannot recognize that there is a difference between that. Most of the time, this approach is good if we have a combinatorial algorithm, if we have a nicer algorithm to solve this. Yeah, but that we saw last time, right? That we will have a margin because they are not tight.
So this is still not the complete residual graph.
No, okay. So now what we are doing is we take the original graph, and in that graph we have a kind of a forward edge. If the, oh, okay, sorry, what I have done wrong is, I think that is why probably there was a confusion. This was my original solution of this, call it Fe. And this is my restricted condition on the restricted primal.
For the remaining, there is no restriction, right?
For remaining, there is no restriction, right? So now, in my new graph, I only are going to have edges wherein my feasible solution either Fe star was equal to C or Fe star was equal to 0. Okay, so then this is opposite of this, like, right? So we are going to have a graph where I will have a forward edge if Fe was equal to 0. And I am going to have a backward edge if Fe was equal to C. Correct? Now, this is the restricted graph, and my question is, what am I asking by this LP in the restricted graph commutativity? Remember, I want to show that this V is not equal to 0. If 0, then optimal. If V is not equal to 0, then there is a flow in this graph, right? That means there is a path between S and T. So, solving restricted primal, finding a feasible solution to it is basically same as finding a path in the undirected restricted graph. I can just find a path from S to T, and if I find a path in S to T, then I am done. So what you will show in the exercise is that an augmenting path, and I will tell you what an augmenting path is. This will again lead back to the solution, the original definition of residual graph. If you have an augmenting path, it gives us a solution for restricted primal. So what is an augmenting path? So this equivalence you can show, and the point is that solving this restricted primal amounts to finding an augmenting path. Okay, so then your problem reduces to undirected graph. And how do we find a path in the undirected graph? Exactly. So this you can solve by DFS, BFS, whatever is your favorite method. The only thing is now you will have to modify the DFS or BFS slightly, so that you keep track of the path and how much flow you can push it in. Sounds good? So once you modify this, and depending upon what you choose, sometimes your algorithm will be very efficient. It can stop in required number of times. Sometimes it can just not converge. Okay, so things are simpler when your capacities are integer. Okay, you start with a integer flow, then you can assure that every time you will get a flow of at least 1, and then you can give better bounds here. If the values are irrational, in some of these cases you might get into keep improving the result, but not in a good amount of time. Okay, so now I will just outline the BFS based approach. You create a queue and you start with the source being in it. Okay, so this is your starting thing, and then you start labeling vertices. Correct? If finally T becomes labeled, that means there is a path, right? So this queue is just to keep track of which neighbors to scan next. This is not the list of labeled vertices that you can keep in some array or something or whatever. This is just telling you what to label, right? So now I will put all the unlabeled vertices of S in the queue. Okay, I'm going to label them. How am I going to label them? So let's say I am scanning X. I am looking at neighbors of Y, and now this is an edge, and this was in our graph because fxy was less than or equal to cxy. Then I say that I am going to reach Y from X, and the flow which can go in Y is minimum over X comma fxy. Okay, so on this path, the amount of flow I can put in is how much flow I can get up to X, either that or the capacity of this edge. The minimum of that I can make it flow. If xy is an edge because fxy was greater than or equal to 0, sorry, fyx was greater than or equal to 0, then sy is equal to x. You will reach it from X. Remember, this is an undirected graph. We are finding a path. We are saying we will reach from X to Y, and Fy is going to be okay. So this is just a modified breadth first search, which allows us to find an augmenting path. Once T is found, then I can stop. then I have a feasible solution. I have a feasible augmenting path, then I have a feasible solution for the restricted primal. Okay? And now, using this augmenting path, I know this is very commutative, this is very intuitive, right? On every path I have seen, oh, there is this much gap, I can push in more things. So the final ft here will tell me how much flow additionally I can put in. So this will tell us even actually the improved primal. Okay. So this primal dual approach works here. There are primal dual approaches for even semi-definite programs. We are not going to cover this in the course, but even works for semi-definite programs. I don't know, there's this paper by Satyen Kale which I had given as a project. Okay, so you probably will talk about this. Okay, so how to apply this in the semi-definite program. There's also, so that is why this primal dual approach is kind of nice. It is not a solution for everything. Again, important point is, it's an approach. I wouldn't call it an algorithm. In some cases, it's worthwhile to take this approach. In some cases, it doesn't help us. Specifically in MaxFlow, when we take this approach, the restricted primal turns out to be something which we know from before. It is this idea of augmenting path.
This is kind of like the Ford-Fulkerson.
This is exactly, that's what I'm saying. This is Ford-Fulkerson algorithm with the perspective of primal dual. It is not at all different from Ford-Fulkerson. What the things which I told you here, this is a literature on Ford-Fulkerson. Okay, I'm just giving you a twist on how to view Ford-Fulkerson algorithm. And this twist is important because this can be done in other linear programs, semi-definite programs, and so forth. Right? So the takeaway from today is the complementary slackness conditions sometimes can help us give a simpler LP, which will let us improve the solution. This kind of approach is known as primal dual approach, and there are many cases when this turns out to be beneficial for us. Okay, this is it for this primal dual approach. Now I want to come up with cases when actually the integer linear program and linear program have a gap. Even if they have a gap, can we do something about it? This is a very interesting idea of relaxation and rounding, which we start from tomorrow.